the remaining time we have, we're going to talk about forces and Newton's laws. So there are 3 laws. Newton has 3 laws, 1, 2, and 3. We're going to talk about what they are. Now, previously, we have learned about how things move, and that's kinematics. That's acceleration, velocity, and displacement. Now we're going to learn about what causes things to move, or why things move, and that's dynamics. When we're talking about pushes or pulls, we talk about forces. There's lots of different forces. Old style forces all got their own variables. They got an N, and they got a W, and they got a big G. We don't use that anymore. Now we use subscripts. We use F sub N, we use F sub W, we use F sub G, force of weight. And then later on, we're going to use F sub B, F sub F, and a bunch of F subs. So if it's a big capital F, it's a force. Okay? So force, we're going to call this force normal, force weight, and force of gravity. Forces are measured in newtons. Now a newton is a tiny amount of force. It's a tiny, tiny, tiny push. Okay? It is the, we'll get there, never mind. I don't want to go, I don't want to get to what a newton is just yet. Other than to say, it is the weight of 100 grams on you. So 100 gram weight, you use 100 grams is 118. Yes, it's about 100 grams. So this is 100 grams. It's the weight of 100 grams pulling at 10 meters per second. So not a lot of force. If you're curious about how much force that is, 100 grams, it's the weight of 100 grams. Not a lot. It's very small. Okay. So for instance, your weight is probably in the neighborhood of 800 or 500 to 1,000 newtons. Okay. I weigh almost exactly 1,000 newtons. Yeah, almost exactly. If you're smaller, you weigh 400, 500 newtons. So a single newton is a pretty small number. Okay, any questions before we jump right in? Anyone who know who that is?
There's a glare right over us.
Yeah, it's the second man on the moon. Yeah, you saw the movie, yeah? There's a movie, The First Man.
Oh, yeah.
So that's Buzz Aldrin.
Yeah.
Actually, I didn't know the rocket scientist.
He punched a guy in the face for saying the moon landing was fake.
Oh, okay, that's cool.
You did what?
I haven't seen the movie. It's probably all Hollywooded up. And then this is an example of Newton's third law. For every action, there is an opposite and equal reaction. So you're riding a motorcycle, you try to kick somebody's door. If you apply 200 newtons of force on the door is going to apply the same 200 newtons of force back on you. So there you go. This is why I have a dash cam. Okay, so quick kinematics review. You don't need to write anything down. Just want to quickly review where we were. We were talking about changes in velocity as acceleration times time. So a change in velocity is acceleration times time. We were talking about a change in velocity when there is no acceleration. That's when we use the d equals vt. Most classically, dx equals vxt. You can only use that when you have no acceleration. And then if there is an acceleration, then you use the free fall formula with the vit. So d equals vit, or v naught t, plus 1/2 at squared. That's when you do have acceleration. So the velocity is actually changing. And then, of course, should you find yourself in a situation where you have velocity, acceleration, and displacement without time, you can use v naught, or vf squared equals vi squared plus 2ad. So those are our famous kinematics exercises. Now we're going to add a few more, and we're going to replace that a with something else. Okay. We're going to learn what causes acceleration. And the thing that causes acceleration is, from your notes, a what? From the concept crossword?
Unbalanced
forces.
Exactly, unbalanced forces. So when you have unbalanced forces, those create acceleration. Now, the great example of a balanced force is what you're doing right now on your chair. Okay. Who is falling through their chair? Anyone? No. Who's being launched out of their chair? Anyone? Okay. So an unbalanced force would cause you to accelerate. A balanced force causes no acceleration. For instance, you're all applying a butt force on your chair, and your chair is applying what we're going to call a normal force back on your butt. And hopefully those two things are equal. Because if they're not equal, you will either accelerate through your chair, or you'll accelerate out of your chair. Yeah. Okay, is gravity a force? No, gravity's not a force. Gravity is an acceleration. Weight is a force. And so this is the old way. Oops, I can't believe I still haven't fixed this. I think I just left this here so you might see this. Capital W is how weight used to be expressed. We don't express it that way anymore because we use capital W for something else. We express it as Fg, force of gravity. And the force of gravity, or the weight of something, is simply its mass multiplied by whatever gravitational field it happens to be in. Now, you and I, hanging out at 2,500 feet, it's about 800 or 750 meters above sea level, we encounter a force or acceleration of gravity about 9.8 meters per second squared, which of course we're just going to round up. So if you're curious what your weight is, if you know your mass, you just multiply your mass times 10 and you get your weight. If you're curious about what your mass is and you know your weight, you just divide your weight by 10 and you get your mass. If you're curious what your mass is or your weight is in SI units, if you take pounds and you multiply by divide by 2.2, that's your mass in kilograms. Yeah.
So to clarify, the capital W isn't written as F with a subscript W?
It's usually F sub G, force of weight, force of gravity. So we usually skip the W and just replace it with F sub G, force of gravity. So if you have a weight of 220 pounds, you have a mass of 100 kilograms. So take your American weight, divide by 2.2, that's going to be your SI mass in kilograms, which is actually kind of fun. We'll talk about force of gravity later. Okay, so here's a fun little exercise. It's not a trick question. Which has a greater weight, a tennis ball or a basketball? A basketball, yeah. If you are not sure about that, next time you go play tennis, bring a basketball with you and try to hit it. It's not going to work out well for you. So which has a greater downward acceleration when you drop them? They're the same. Yeah, they're the same. Okay, so Galileo proved that before, or famously proved it. This is kind of apocryphal. The idea is Galileo took a large ball and a small ball, or a large rock and a small rock of similar materials, and then he put two physics students down below, and he dropped them, and did he hear, ow, ow, or did he hear, ow? Yeah, he heard, ow, because they hit at the same time. Okay, so Galileo believes that. Now, before Galileo, it was believed, and again, apocryphal, it's just a story, it was believed that Aristotle projected the idea that things had natural motion, that they naturally moved in various ways, and large objects had more natural motion than small objects because there was more stuff. So the natural motion of something in air is to fall towards the earth. So he believed, and he was a philosopher, not a scientist. Philosophers didn't do experiments, they just thought about stuff. That's the way it was for thousands of years. Up until Galileo and John Dalton and all sorts of other cool guys. They just thought about stuff, they never actually tested it. So the general idea is a large object had more natural motion than a small object, so it would move faster towards the earth. We find out later on, through Galileo, that no, all objects pretty much fall at the same rate when you ignore air resistance. And we'll talk about air resistance a little bit later today, or later tomorrow too. Okay, any questions? No, moving on. No.
Oh no. Oh, guy. Oh my gosh.
I love animated gifs.
I love it.
So, dynamics is the name that we attach to the study of forces and their interactions. Dynamics literally means the study of power. Dyna means power or strength. Something that is dynamic happens very quickly. Think dynamite. Dynamite is a name for a material that blows up. Okay, so it was named dynamite like this is power material, power mineral. So let's call it dynamite. So dynamics is literally the study of how forces interact with each other. So forces are pushes or pulls. Forces are vectors. Forces are vectors. This is important. Forces are vectors, meaning that you can add them up as long as they are in the same coordinate plane. Okay. They will interact as long as they're in the same coordinate plane. So we learned about in two-dimensional motion that x motion does not interfere with y motion. Y motion does not interact with x motion. Similarly, a force in an x direction does not interact with a force in a y direction because they are vectors. So if you have one force vector aimed, one force vector aimed that way with a plus x magnitude, and one force vector added that way with a negative x magnitude, the resulting vector is just the sum of those two things. The resulting vector is the sum of those two things. Just take the x plus the negative x, and you get a resulting x. However, if you have a vector that has a plus x that way, and a vector that has a plus y that way, you cannot sum them up. What must you do to find the resultant? Yeah, the Pythagorean theorem, right. So the x vector and the y vector, you can't add them up. The only way you can do that is just like we adding vectors, you can use the Pythagorean theorem to find the resultant xy vector. Does that make sense? So this is the reason we learned vectors, so we can add them up. And this is also, if you were to draw a vector of you sitting down in your chair right now, so there's your chair, and here's you. Actually, here's a table. Here's your hands, and then here's your legs. There you are, and your feet. Apparently you don't reach the bottom, so you're very small. So if you were to draw two vectors representing you, one would be the FG pointing down, and the other one, we have an anchor point, the other one would be what's called an FN, or force normal, pointing up, and hopefully they would be the same magnitude. Because if they weren't the same magnitude, then those two vectors would add up and have some sort of resultant vector that would have you accelerating either through your chair or off your chair. Does that make sense? Okay. I smell something funny.
Gas.
Doesn't smell like gas. Okay. So any questions so far before we move on? So common forces, we talked about weight. Weight is F sub g, mass times the acceleration due to gravity. And then the normal that I've been talking about gets an F sub n. The normal force is a resisting force. It's the force that molecules produce to keep from getting moved, keep from getting squished. The molecules of your chair, the plastic part of your chair and the metal part of your chair, and as they connect to the floor, those molecules are what's actually producing the normal force, which is acting against your weight. And the normal force is pretty cool. I'll show you some examples when you're done scribbling. Let's say that table, let's say, I think it weighs about 60 pounds. So let's say that 60-pound table has a mass of 120 kilograms. Okay. Then let's say that 120 kilograms, actually not 60 pounds, 30 kilograms. Say it has a mass of 30 kilograms. And let's say that 30 kilogram table is exerting a force weight on the floor of 300 newtons. Make sense? What is the normal force the floor is exerting on the table? 300 newtons. So if I take my 10 kilogram toolbox and I put it on the table, now the table has a mass of 40 kilograms. And it exerts 400 newtons on the floor. How much is the floor exerting back? 400 newtons. The normal force is not a set value. It has an upper limit, but it's not a set value. The normal force will constantly adjust to resist whatever's pushing against it. But again, it's not a set value. It can change. It has an upper limit, but it can change. For instance, if if Lane was sitting on his chair, we're going to say Lane's weight down is equal to the chair's normal force up, right? Now, if Bowen and Aaron jumped on Lane and added their mass to Lane's mass to the chair, there's a very good chance that the chair will no longer be able to produce a normal force that would be required. And what's going to happen to the Bowen, Aaron, Lane system?
It's gonna fall.
And by fall, you mean it's going to
Accelerate.
It's going to accelerate. Because suddenly, the downward weight of the three people is suddenly larger than what the normal force of the chair can produce. Now you have an unbalanced force, you have a downward net force, and that produces a downward acceleration. Make sense? By the way, net force is the term we use when we add forces together. So if this was plus 10 and this was minus 8, the net force is plus 2. Net force. Net's just one of those words, so like you have net money. You're like, well, I bought the thing for 60 bucks, but I sold it for 80 bucks, so I have a net profit of 20 bucks. Net. Okay, then there's friction. Friction is intermolecular attractions or intermolecular repulsions. It's intermolecular interactions between materials. Intermolecular means between materials, between molecules. It can be static or it can be kinetic. So the friction types, there's lots and lots of friction types. They all are similar in that they all... Yeah, we gotta work on this thing because a lot of the gas actually went through the capacitors. The friction type, it's all interactions of clouds of electrons with each other and different materials. Now, static friction is the friction you get when you try to push a refrigerator. Anyone ever tried to push a refrigerator to get a refrigerator to move?
Yeah.
Static friction is pushing against it. But once you get it moving, then kinetic friction is what you must overcome. So first you're pushing on something, first you have to overcome the static friction, then once you've overcome that, then you continually overcome the kinetic friction. You've encountered this, right? Pushing a dresser or something?
Yeah.
Well, if you were to graph your friction, and like you're going to apply a force on something, you're going to apply a force, apply a force, apply a force, you're going to keep applying more and more force, suddenly you have to apply less force. It's going to look like this. Right? So this is the friction that is kinetic you have to overcome. This is the friction that is static that you must overcome. Once you overcome your static friction, then all you have to overcome is the kinetic friction to get it to keep going. My question to you is, why? Why do you have to overcome the static friction, and why is the static friction always larger than the kinetic friction? Anyone have an idea?
Doesn't have kinetic energy.
Okay, so you're giving it kinetic energy, that's a good point. But why do you have to, why is the static friction always larger? There's a word I'm looking for, and it starts with an I. Inertia, exactly. So when you're pushing on something, you have to overcome inertia. So there's static friction, and you have to overcome the inertia to get it to move. But here's the cool thing. Once you get it moving, inertia goes from working against you to working with you. Yeah, because inertia is, this is the first law of Newton's first law of forces in motion. First law of forces in motion. For every, once you get something going, it wants to keep going. But it doesn't want to keep going to begin with. An object at rest tends to stay at rest. An object in motion tends to stay in motion. A student at home tends to stay at home until acted on by a parent. Go to school. Or a student at a party tends to stay at a party until acted on by the police. Go home. So that's inertia. So with static friction, you have to overcome the static friction. You have to overcome the inertia. Once you overcome the inertia, you continually overcome the kinetic friction, but the kinetic friction is easier to overcome because now inertia is working for you. Make sense? That's the universe. Okay. This is a good place to end. A white cat and a brown cat are walking on a roof and start to slip. Which cat slips off the roof first? Wait for it. Wait for it. You can stop waiting. There's a formula for friction force. And it's like this. The force of friction, F sub F, is equal to mu Fn. Mu. That's the Greek letter mu. It's like a lowercase u that starts below the line. So if this is your writing line, a mu starts below the line and then ends on the line. If you want to see that again, I'll do it slower. You start below the line, then you end on the line. That's a mu. Okay. So it's a Greek letter. It's used, unfortunately, in about half a dozen different science environments. But today, we're using it to represent the coefficient of friction. The coefficient of friction. The coefficient of friction is a number between 0 and 1. And it literally is how much friction exists between two surfaces. The coefficient of friction between water and metal is very, very low. The coefficient of friction between metal and concrete is very, very high. Okay. Coefficient of friction between steel and steel is actually pretty high. Metal on metal is very, very high. This is why locomotives work. Trains, they have metal wheels. The reason they have metal wheels and why they work is steel on steel friction is exceptionally high. Okay, so force of friction depends upon the materials, but it also depends upon the normal force. Make sense? So if I asked Taylor to push Heidi out of her chair, she could probably do it, because all she has to overcome is the normal force on Heidi, which is equal to Heidi's weight, because Heidi's weight down and normal force up are the same. So if I said, Taylor, please push Heidi off her chair, she could probably do it, because she only has to overcome a friction coefficient multiplied by Heidi's weight. Can you see that?
Yeah.
On the other hand, if Braden and Emily and Sarah all jumped onto Heidi's lap, now there's a lot more normal force. It's going to be a lot harder for Taylor to push the four-person combination out of her chair.
Four-person pile.
The four-person pile. Okay, does that make sense?
Yeah.
Okay, so friction force depends upon the materials that are in contact and the normal force you have to overcome. We're going to do a lab and we're going to learn about what happens to normal force at an angle. We've got a whole bunch of really cool pieces of equipment that we're going to play with probably Wednesday. Yep, Wednesday. Okay, questions? All right, this is a good place to stop. We'll pick this up again tomorrow.